In order to retrieve the saturated liquid density data for tetrahydrofuran, I'm first starting the jump start here and go to Dortmund Data Bank. I use add search component, search for tetrahydrofuran, just a part of the string, and I find it here. Okay, we can also click on this link and see the physical properties, and here they are. We might need them later, so I'm just making this small. Now I go to system exact match. Here are now all the data. This is PCP. PCP means pure component properties, and we also have all the empty data sets, which means the ones that are in the full DDB but not in this free version. I click this off. Now we see only what's available in the free version. I go to density down here. These are the data, all liquid densities, and I can mark them. Like in the Explorer, like you mark files. I go to predict. It found that they're all in the liquid state. Temperature versus density for the axis is okay. And here is only method Campell Thodos. In the full version you would have more methods. Now it calculates and it gets these results in kilograms per cubic meter, and we see here the experiment, the calculation, the deviation. You can get a data grid for spreadsheet calculator and plots. This is the absolute and relative deviation, and we can see the deviations get high at high temperatures when this component is approaching its critical point. And otherwise it's pretty good here, and the standard plot would be this one. Now we can enter artist and have a look which methods are available there. So I go to jump start, property estimation, artist. I still remember that the molecule was 159, the number, so I can just directly go here to DDB 159. So calculate, and I would go to densities and volumes, liquid volume. Here's the liquid density and Campell Thodos. We saw that already. There were a few others but not available here. But now I can go to the liquid volume, and at the normal boiling point there are two more methods, Schröder and Lebar. So I click on calculate, and what I'm getting here is cubic centimeters per mole, but before we had a density given in kilograms per cubic meter. Okay, so let us have a look at our number, kilograms per cubic meter, in this plot. That was a normal boiling point, so now we need to know where the normal boiling point is. I'm going back here to that was a query. Here is a component window, and the normal boiling point is here until the Anton constants 339.12 and 339.12 is somewhere here in this range. There's a gap in the data, so I zoom in. 339.12 is somewhere here, so we would be somewhere here, which is about, when we look on the left side, 837 kilograms per cubic meter. Now, how do we convert them? We should divide the molecular weight by this number. The molecular weight we get again here from the component, which is 72.107. I copy that. Now we need a small calculator. There's a free tool by Microsoft Mathematics. And now we take the molecular weight and we divide it by this 837, and the result is 0.086, and now we remember that was gram per mole, and this was kilogram per cubic meter, so we end up gram kilogram, so to have kilogram should be divided by 1000, and we would get 86.14 cubic centimeters per mole. 86.14. And now I look at artist, and $86.14. Again, I have to calculate. Is quite good in the middle between the two methods here.